So one of the first things you need to understand when you do rotation problems is a new measurement, an important measurement called the moment of inertia. It's also sometimes called the rotational inertia. You'll hear that different times from different resources, different textbooks use different ones. I kind of use them interchangeably. And the reason this is so important is that this is basically, for rotation, what's analogous to mass for just normal linear motion. So everything we've ever done with mass, for example, Newton's laws, F equals ma, or momentum, we're going to have to do instead with what's called moment of inertia. So we use the symbol I, which actually is a pretty sensible symbol compared to a lot of symbols we use in physics. And the calculation is not that hard. I'm hoping that you're watching this soon after watching my video on the center of mass, because I've got the same arrangement drawn on this video that I drew there, just to show you the difference in the calculation. So for calculating a moment of inertia, first of all, you have to specify the axis around which you want to calculate it. Because what we're imagining here is that we're trying to rotate something. And this moment of inertia gives us a feel for how difficult is it to start or stop or change the rotation about a particular axis. So I've got a couple axes drawn here. I've got the X and Y axes. And I'm also going to imagine for my first example, the Z axis would be just coming out kind of towards us here. So we're going to do that one first, and then we'll do the X and the Y. But once we specify that, then here's what you do. It again is a summation, kind of like center of mass is, but all you do is you count out how many parts you have. We call that N. And each part gets named 1, 2, 3, 4, 5, or whatever. We use a symbol I for that number. It's just a counting number. And we take the mass of that part times the square of the distance that that part is from the rotation axis. Okay, the nearest point to the rotation axis. So that's why I'm going to show you 3 different examples so you can see how our choice of rotation axis really matters. So the easiest one to do here is showing how we rotate along the axis that comes out towards you. We'll call that the z-axis. So I'll refer to this as the rotation inertia about the z-axis. That's the phrasing we use, about the axis. So if we count up our pieces, we have 4 pieces here. So we're going to have 4 things to add together. Each one will be, and I should have put an I on this, each one will be included with a mass and the square of the distance that that mass is from the rotation axis. So I'm going to have 4 things. My first one I'll just do up here. This is a 4 kilogram mass. And how far is it from the rotation axis? Well, it's 3 meters away. That's what I marked there. So that's 3 meters, and that has to be squared. And then we go to the next piece here. Now, the 2, that's right at the rotation axis, so my R would be 0. So I'm just going to say, well, I guess I'll go ahead and write it. 2 kilograms times 0 squared. It seems kind of silly to write that, doesn't it? And then my other 2 pieces, here's a 1 kilogram mass that is 3 meters away from the z-axis. And here's another 1 kilogram that is 6 meters away from that axis. So I've got 1 kilogram times 3 meters squared plus 1 kilogram times 6 meters squared. That's a lot to fit on there. And you see here, we're going to get just a number. This is not a vector like center of mass is. It's just a number. So I'm going to grab my calculator and do this calculation, and we'll see what we come up with. Well, my calculator gives me 81. And look at the units there. They're a little unusual. 81 kilograms meters squared. There's no short notation for that, unfortunately. You just have to say kilograms meters squared. So again, we don't give a direction because it's not a vector. So what happens if we are trying to rotate this around the x-axis? So imagine, here's your x-axis. Imagine you're trying to spin it. I hope this shows up well in the video. In a fashion like this. So I'm moving kind of towards the camera and away from the camera. So let's think about this. What mass is actually going to end up moving there? All of these 3 are right on that axis. In other words, their R would be 0. It's because they're not really moving. The only mass that's moving would be the 4, and it's making a nice 3 meter radius circle as that spins around the x-axis. And so we only have one of the four terms that is anything but 0. So again, just for being explicit here, I can say 3 of my terms end up being 0, and the fourth one is the mass times the distance it is from the axis, and that's 3 meters. That gets squared. And along the x-axis then, that would be 9 times 4, or just 36 kilograms meters squared. Again, that's the moment of inertia for rotating it about the x-axis. And what if we're going to spin it around the y-axis? Now we're going to imagine these two basically being stationary. They might kind of turn a little bit just on their own axis, but they're not moving anywhere. But these two are moving in big circles. This guy making a 3-meter radius circle like that. This one making a big 6-meter circle around that. And so around the y-axis, we again would have two terms that would be 0. These two have an r equal to 0. And then we take each of the other masses times the square of their distance from the y-axis. So this would be 1 kilogram times 3 meters squared, and another 1 kilogram times 6 meters squared. Might not need a calculator for that. That's just 9 and 36 for a total of 45 kilograms meters squared. So you see what's important here is that there's no such thing as the moment of inertia for an arrangement. There's an infinite number of moments of inertia. You always have to ask, well, what are you trying to rotate it about? What axis is that? We could even, although this would be harder, I thought about doing this on the video and thought it would take too long. This would be a fun little exercise for you, though. What if we were going to spin it around the axis right here, kind of the axis that comes out parallel with the z-axis, but shifted over 3 meters? See, then this guy would not have any r, but the other three would. Now, what makes this a little harder is we would need to know this distance here, because you have to know the nearest distance from your axis to each of your masses. It's a little harder when you've got a little angle involved. You just got to do a little triangle math. So I'm not going to do that just because I don't want to take the time. But I think what I've shown you here is a pretty good example of how we do these, what we call discrete number of particles. So if we have 3 or 4 or 5 things, that's easy enough. But what happens if you have things that aren't just made up of little pieces? That involves a little calculus. And although most textbooks know that you might be a little new to calculus and they don't expect you to do it yourself, so almost all of them have a little cheat sheet in the book, a chart of some type that shows you what the calculus will give you in case you can't do it yourself. But in another video, I'm going to show you how you would use calculus to get those expressions yourself, and then also how to use the shortcut that the textbook provides. So check out that video for the rest of the moment of inertia. Thanks for watching.